This is Dr. Jack Jackson with part 5 of our series of lectures on descriptive statistics. This one is on the measures of variability. When we're measuring variability, we're measuring the amount of spread or variation that a data set has. Of course, the opposite of variation is consistency. So if it's high variable, it's widespread and low consistency. Okay, low variability would be a narrow spread and highly consistent. So when we want to measure how far spread out the data is, those are called measures of variability or spread. We're going to look at 4 different ones. These are all numbers, statistics, if it's a sample, that tells us something about the variability or spread. The easiest one is the range. We'll also talk about the mean, absolute deviation, the variance, and the standard deviation. Let's start with the range. The range is the easiest one. It's the maximum minus the minimum. It's the distance from the minimum value up to the maximum value. So it's a measure of how spread out your whole data set is from the bottom to the top. This is the most simple of all measures of variability, and because it's so easy to compute, it is often used. But in a way, it's not very sophisticated, because notice it does not take on or take into account any of the data values in the middle. Only the ends, the minimum, the maximum, only those extreme values have anything to do with the range itself. Now, by the way, let's be careful about this word range. The range is a single number, not an interval. So if the data set went from 1 of a minimum to 11 of a maximum, that would be a range of 10. The single number 10 is the range, not the interval from 1 to 11 or something like that. It's a single number. So this word range is not the same as the range of a function, like you may have studied in your algebra class, or a range in Excel is a little bit different setup. So a statistical range is a little bit different. It's a single number. And notice once again, it only depends on extreme values, and the other values, none of them have any effect at all on the range. So in a way, it's kind of a crude measure of how variable your data is or how spread out it is. But it doesn't take into account how variable the stuff is in the middle between these extreme values. As we look at the dot plot of our inauguration age data, we can see the range as the distance from the minimum to the maximum. 69 minus 42 equals 28, so the range is the single number 28. So there is a 28-year span from the youngest president to the oldest. By the way, the youngest was Teddy Roosevelt, and the oldest, Ronald Reagan. The interquartile range is similar to the range. The range was the distance from the minimum to the maximum, how far spread out all the data is. The interquartile range is the distance from Q1 to Q3, from the lower to the upper quartile. So the IQR, for short, interquartile range, is Q3 minus Q1. So it's the distance between the upper and lower values, quartile values. It measures the spread in the middle half of the data. In other words, it's the length of the box in the box plot. Okay, now let's start looking at a couple of more sophisticated measurements that take into account a lot more of the data. First one we're going to look at is called the mean absolute deviation. So to do this, let's start with a data set. Now, by the way, I will admit this is a very contrived data set because some of these calculations can get a little bit nasty by hand if the data set gets very large or some of the calculations are a little bit bad or whatever. So particularly, I have a data set here. You can see it with the purple background. The x sub 1 is 4, x sub 2 is 5, x sub 3 is 8, x sub 4 is 10, and so forth up to x sub n. X sub 10 is 27. So we see we have 10 data sets. So the k is just a counting variable, counting number there, and the x sub k are the actual data values. So these are the data values right here, 4, 5, 8, and so forth. Of course, we could find the range pretty easily. 27 minus 4 is 23, so the range is 23. Now, one thing we can also find is the mean. So we add all these up, and we get 120. Divide by the number of data points, 10, and you get 12. As I said before, I made this data set up very nicely, so when we divide by 10, it was easy to divide. I made this sum a multiple of 10, so this comes out to be a whole number here, just to make things easy. So again, here's the formula for the mean. Add them all up. So there's the k. Here's x. Here k is 1, x sub 1. K is 2, x sub 2. K is 3, x sub 3. K is 4, x sub 4 is 10. K is 5, x sub 5 is 11. So add up all the x sub k's and you get 120. That's the numerator right here of this formula, the sum of the x sub k's, x sub i's, I've got them here. So whether we call it I or k, same thing. And n is 10. We're going to divide by 10, and that gets us our 12. So 120 is the numerator, 10 is the denominator. Divide out, x bar is 12. That is the mean. Okay, so now what do we want to do with the mean absolute deviation? We want to see how things are spread out from the center defined by the mean. So we want to take the mean, which is a measure of the center, see how far things are spread out from that. So we want to see if we want to find how far apart two things are, you just subtract. So let's do that. Let's take each data value minus the mean. So if we do that, take the x sub k's minus the x bar. Remember, x bar is 12. So 4 minus 12 is negative 8. 5 minus 12 is negative 7. 8 minus 12 is negative 4. And so forth. 12 minus 12 is 0. Down here we get some positive values. 27 minus 12 is 15. So we interpret this as a 0 value means that data value is at the mean. So that the mean actually shows up in the data set in this case, 12. That doesn't always happen, but it did here. We have some negative values. Those are data values which are below the mean. And we have some positive values that are above the mean. So when you see this deviation from the mean of negative 7 right here, that says that that data value, 5, is 7 units below the mean. Whereas this 15 down here for the deviation says that 27 is 15 units above the mean. Now, we add all those up. Look what you get. Oh, we get 0. Well, that's interesting. It turns out you always get 0. In fact, this is one way we can interpret the mean. It's a data value, it's a place, so that the deviations from the mean, if you sum them up, you always get 0. Well, so that means that's not very useful for us then, because if it's always 0, that doesn't tell us anything from one to the other. So what do we need to do to this? Well, what we need to do is we need to make these things positive, because we don't really care if it's above or below the mean. It's still spread out from the mean the bigger it gets. So there's two ways to go about making these things positive. At least two ways. And one is to take the absolute value, and the other one is to square them. And each of these leads to a different type of measure of variability. The first one we're going to look at is taking the absolute value. That's the deviation part is the differences here. The absolute part is that we're going to take the absolute value of these. So the next table, add another column. Same table as before, but now we've taken the absolute value of all these. Of course, the absolute value is a piecewise defined function. If the number is 0 or positive, it leaves it alone. If it is a negative number here, we send it in for a little operation, have its negative removed, or multiply it by negative 1. And so we get all positives here. Now when we add them up, we no longer get 0, we get 46. Now, just using the 46 here, the sum of the absolute values of the deviations, that wouldn't be too good, because the more data values you have, the bigger this would get. So for example, you could have a million data values that are all within one, let's say they're all 1 unit away from the mean. that would be a very consistent data set, and yet it would have a sum of absolute deviations 1 million. It'd be really big. Whereas you could have a data set like this that's not nearly as consistent, but with only 10 data values, this absolute value is not, the sum of the absolute values is not very big. So what do we need to do? We need to average this out. On average, how far are the data values from the mean? That's what this mean absolute deviation, MAD, that's what it measures. It measures on average how far are the data values from the mean. So we're just taking this sum of 46 divided by 10 to get 4.6. That is the mean absolute deviation. So here's the formula for it. Take each of the x sub k's, that's the ones in the second column here. Compute the mean first, that's our 12. Take them and subtract, that's this third column. Take the absolute value of each of those, that's the last column. Add them all up, that's the 46. That's what this summation symbol means, add them all up. And then divide by how many you have, in this case dividing by 10, and that gets you this 4.6 over here, which is the mean absolute deviation. So on average, this data set is 4.6 units away from the mean. Now if you have a population, it's the same thing. You'll use mu for the population mean, capital N for the population size, and you'll use this formula here for the population mean absolute deviation. And if you did the same thing for a sample, then you're using x bar for the sample mean, which is the way I'm thinking of it here, and little n for the sample size. And so that's your lowercase MAD, mean absolute deviation. Okay, let's look at another example. So we're going to back this table up to where we have the first three columns again. And we're going to look at that to see the variance and standard deviation. So we recall that when we're working with the mean absolute deviations, we needed to turn the deviations into positives. The method we chose for the mean absolute deviation was to just take the absolute value. But another, actually more useful alternative is to square the values at that point. Now why do we prefer this? We prefer this because absolute value is really a piecewise defined function. It says if your input is a positive or 0, you do one thing, that is, leave it alone, keep it the same. Whereas if the input is a negative number, you do a different thing, that is, you multiply it by -1. So sometimes you multiply by -1, sometimes you don't do anything to it. So because of this dual nature, this piecewise nature of the absolute value function, it makes it harder to work with. It makes it harder to do things like algebra and calculus and so forth with it. It's harder to manipulate the formula. It's just a little bit harder to work with. Whereas the squaring function is really nice. The squaring function also turns things positive, also changes their size. But what it does is if you just multiplies the number with itself, and it does the same thing to it regardless of what the input, whether the input is a positive, negative, or 0, you just square it, you're multiplying by yourself. So it's a little bit easier to work with, and that's the main reason why we use it. It makes it easier to do things like algebra and calculus and other things with it. Okay, so the squaring function is what we would rather do here. Also makes it a little bit more sensitive to extreme values, which is not a bad thing for what we want to do here. So far we're back to our same table of data. The first three columns are exactly the same. But this time, instead of taking the absolute value to get the last column, I'm going to square them. So the first column is just a counting number, k. The second column is your data values, x sub k. So this is x1, x2, x3, x4, so forth, down the table. We take the mean, x bar is 12. So add those up to get 120, divide by 10 to get 12 once again. Take that 12, subtract it from each one of these. So you're taking the xk minus the x bar to get these, same as before. Now we take each of these and square it. So now we have the xk minus the x bar square. Once again we add it up, and once again we just average out these things. Add them up, and then divide by how many we have. So if you have a population, this is called the variance. This is a capital letter sigma, which means add them up. So we take each x sub k minus the mean, square it, add them up, divide by the population size. So let's go over that again. X sub k, that's the data values. Subtract off the mean, 12. Get those differences. Square each one of those. Add all of those up. So we squared them. That's the third. So this is the second column for the xk. The third column for the xk minus mu's in the parentheses. Square them. Now we're out to the fourth column. Add them all up. So the numerator is adding down this last column. In this case 376. And then we divide by how many data values we have altogether, which is 10. And that's 37.6. That's called the variance. This is a lowercase sigma here, and we actually use sigma squared for the variance, indicating that squaring that's going on that we had in the process. That's called the population variance. Now, notice that our units are off here whenever we are working through this. So if our original data was, say, in inches, then xk would be in inches, mu would also be in inches, subtract, you get inches, but when you square, you get square inches. Add them up, you got square inches divided by the number you got, that's still square inches. That's sort of the wrong unit. So to switch it back to the correct units, we take the square root of the whole thing, and that's called not longer sigma square, but sigma. So sigma is the population standard deviation, sigma square is the population variance. Now you notice I've been saying population over and all. Now what if we have a sample? Okay, most of the time we do not have feasible access to a full population. So instead of trying to find the population parameter in this case would be the variance or the standard deviation of the population, what we have to do is use a statistic from a representative sample. And most of the time we're wanting to use that to estimate the corresponding population parameter. So for example, if we want to find the mean of all of the entire population of things that we're measuring, that would be the population mean. Well, most likely we can't get our hands on the data for the entire population, so what we can do is take a sample. And it turns out that the mean of that sample is our best estimate of the mean of the entire population. It's called an unbiased estimator. So in other words, what we're saying about it, it's unbiased. So if we were to do this over and over and over again for lots and lots and lots of samples, that if we average out all those means that we got for each sample, it should come up pretty close to the mean of the true population. But this is not true for variance. It turns out that samples tend to be less variable than the population. So if we use the formula that we did above, okay, so if we go back to here and we use this same formula for standard deviation, or the one before for variance, and this n is the sample n, and this mu is now the x bar, the sample mean, and this is the little n, the sample size, then it would turn out that that way of doing the variance is going to be an underestimate of how variable the actual population is going to be. So if we're going to use that to approximate the real population variance, we're going to pretty consistently underestimate. Not necessarily every time, but on average, it would underestimate the population variance. So we need to adjust the formula a little bit to make it a little bit larger. So one way we can make it a little bit larger is to make the denominator a little bit smaller. Okay? And it turns out that it's just enough if you will subtract 1 from that sample size. That's just enough to make it an unbiased estimator. So that if you did that time after time after time after time again, and you took a sample each time and found its variance using the formula with an n minus 1 there, that would turn out to be, and average those out, that would turn out to be about the same as the population variance if you could do it for the whole population. So, here's how we adjust the formula. The sample variance is the same as the population variance, but notice, of course, we've replaced mu by x bar because we don't know the population mean, but we do know the mean of our sample. And we replace little n up here in our summation, capital N with little n, because we don't know this, or we're not going to use the size of the whole population, we're using the size of our sample. But the denominator, not only is big N is not replaced by little n, but rather by little n minus 1. And so this is the sample variance, and it turns out that the sample variance is an unbiased estimator for the population variance. And of course, if it's instead of a lowercase sigma, it's now the lowercase s. And remember, s and sigma are kind of the same thing. I mean, s is a Roman version and sigma is a Greek version, but they're basically the same kind of letter. And then, so s by itself is a sample standard deviation, and of course it's the square root of that. So this formula right here is the formula for the sample standard deviation. Now, in this course, always assume that you're dealing with a sample unless specifically told otherwise. Okay? Always consider we're using s. So if you, for example, have a calculator and it produces both an s and a sigma, which your TI-84 will, for example, we're always going to use the s. Unless you know for sure that it is a full population of data that you have. Okay, so let's take a look at a couple of data sets. Both the data sets below have, think of this, have a mean of 10. Now assume this has actual probabilities on the side. Assume these are actual relative frequencies. Okay, and actually, if you could multiply those by the sample size, you would get actual frequencies that would go with these bars. So this could be like a frequency histogram or a relative frequency histogram. They would look the same, the scale would just be different on the side. So here we have two of these. Notice that they both go from 0 to 20 on the scales here, just are a little bit beyond 0 to 20, and you can see what they look like. Just by looking at it, you can see that the one on the left is more consistent, has less spread, more consistent, more values near the mean, whereas the one on the right is more spread out, more values spread all the way out. So it has fewer values concentrated near the mean, more spread, more variability. So that means that it has a higher standard deviation. So the one on the right has the higher standard deviation. In this particular case, it's 3. And the one on the left has a standard deviation of 2.24. It has a smaller standard deviation. So smaller standard deviation will hump stuff up and squeeze things up toward the middle, toward the mean, whereas the higher standard deviation will spread things out. So the one on the left, lower standard deviation, the one on the right, higher standard deviation. Now it turns out that we can use the standard deviation, or a z-score that we'll compute in a little bit, to give a measure of relative standing. So for any distribution, the proportion of data values within z standard deviations of the mean is at least 1 minus 1 over z squared, where z is the number of standard deviations we are away from the mean. This is called Chebychev's theorem. So this is something that a statistician could actually prove. Now notice if z is 1 or less, this really doesn't tell you anything. Because if you plug in 1, you got z squared is 1, 1 over 1 is 1, 1 minus 1 is 0. So it says how much are guaranteed to be within 1 standard deviation of the mean. Well, by Chebychev's theorem, well, nothing necessarily has to be within 1 standard deviation of the mean. But this is interesting as we keep increasing this. Z is 2. If you're 2 standard deviations away from the mean, we plug that into the formula. You get 1 minus 1 over 2 squared. That's 1 minus 1/4. We get 3/4, or 75% of the data has to be within 2 standard deviations of the mean, no matter what the distribution looks like. Whether it's kind of humped up in the middle, or more spread out, or humped up on one end or the other. It really makes, or just evenly spread out. It doesn't matter. At least 75% has to be within 2 standard deviations of the mean. If you go out 3 standard deviations, you can see the calculation there. It turns out that 8/9, or about 89%, has to be at least that much, has to be within 3 standard deviations of the mean. If you go out 4 standard deviations, at least 93.75% has to be in there, 15/16. If you go out 5 standard deviations, at least 24/25, or 96% has to be within 5 standard deviations of the mean there. 6 standard deviations of the mean, you get 97.2%, so at least 97.2% is within 6 standard deviations of the mean. So we can, what this does, Chebychev's theorem, it gives us a way of using the really the standard deviation, count how many standard deviations you want to go out from the mean, and you must capture a certain amount of data within that. So notice this leads us to the idea of a z-score. So a z-score measures how many standard deviations we are above or below the mean, and this gives us a measure of relative standing. It also gives us a way to give a rough comparison between items of different types. I'll come back to that in a minute. So z is the number of standard deviations above or below the mean. A positive z indicates the value is above the mean, a 0z indicates the value is at the mean, and negative z indicates the value is below the mean. And the formula is pretty simple. You just take, for a sample, which we'd probably use a lowercase z, it would be the x value, that's your measurement, minus x bar, which is the sample mean, divided by the sample standard deviation s, and that gives you how many standard deviations you are above the mean. Okay, of course, if x is less than x bar, that's a negative number. Same thing, x minus mu over sigma would be capital Z, that's for a population. Okay, so think about it a minute. Again, the x is the data value, x bar is the mean, x minus x mean is the distance above, if it's positive, or below, if it's negative, the mean. And then we want to see how many standard deviations that is, then we divide by s. So a z of 2 means you're 2 standard deviations above the mean. It doesn't have to be a whole number, by the way. You could say the z could be 3.75. And also remember in Chebychev's theorem, I've worked this out for natural numbers from 1 to 6, but you could also use the same theorem to put in a z value of 2.73 if you want, and work this out. Now, Chebychev's theorem is a worst case scenario. This is the worst possible, this is the least amount of data that could be in there. There might be more. So, Chebychev's theorem tells us nothing about the amount of data within 1 standard deviation or less than the mean. It is a worst case scenario. There are distributions where the worst case actually happens, so we can't really do better than Chebychev's theorem if we're going to be completely arbitrary about the and full generality about the distribution. Okay, but many distributions, I would say most distributions, have much higher amounts within this interval. So for any distribution, at least 89% of the data is guaranteed to be within 3 standard deviations of the mean. But if we have data that's mounded up in the middle and symmetric mound-shaped data, that value will likely be over 99%. Now, we also have a specific kind of distribution we'll study about in more detail in a later chapter called the normal distribution, sometimes called the bell-shaped curve or a Gaussian distribution. You can see a graph of the standard normal here in this graph down here. So, if you have a z-score of 1, so we go between -1 and 1 on this scale because the mean is 0. So between -1 and 1 means you're within 1 standard deviation of the mean. Now, Chebychev's theorem wouldn't guarantee anything about that, but for a normal distribution, it turns out that it's approximately 68.27% of the data is within 1 standard deviation of the mean. If you go out 2 standard deviations from over here from -2 to 2 and look at all this part in the middle, and this would give us, well, 95.45% of the data is within 2 standard deviations, from 2 standard deviations below the mean to 2 standard deviations above the mean, if it is actually a normal distribution. Chebychev's theorem only guarantees 75% of the data is there, but in normal, it's much higher. If you go out 3 standard deviations, you can see that nearly all the data is between -3 and 3 standard deviations. Turns out that at least 90 or approximately 99.73% of the data is within 3 standard deviations of the mean, even though Chebychev's theorem only guarantees approximately 89%. If you go out to 4 standard deviations, which is a little bit off the screen that you see here for this one, you get 99.9994% of the data, practically all of it, for in a practical, real-world sense. In most situations, that would be considered practically everything, if it's a normal. But if it's not a normal, Chebychev's theorem only guarantees 93.75. And of course, if you get a shape that's very similar to a normal, that's kind of mounded up and centered up, then we can go more with these numbers on the normal as being approximately the one. So sometimes your textbooks will say things like empirical rule. And empirical rule, what they're doing is they're assuming the data is normal or very close to normal, and so they're using the values from the normal curve. Whereas Chebychev's theorem, if we don't know anything about the distribution, we would have to go with these values for how much is within z standard deviations of the mean. But if it's normal curve or something very close to normal, we would approximate with these values over here. Now let's just talk a little bit about center versus variability. If we look at these examples, consider we've got a marksman trying to hit the center of these targets. And we have 4 different guys shooting these things. Which one is the best one? Well, I think we'd all agree that B is the best shot. Which is the worst shot? Well, probably D. Okay, let's look at the 2 in the middle. A or C. Which one's probably easier to fix? And how are these 2 things different? Well, if you look back at this, you can see that both B and A are pretty consistent. But the difference between A and B is where they're centered. B is centered up where it should be, in the center of the target, whereas A is centered up a little high and to the right. We can improve A pretty easily by just telling the marksman to, let's aim just a little bit further down and to the left, and we might be able to turn him into somebody that's almost as good as B. C and D are both much more variable, so variability is higher. They're more spread out from the mean. They're more inconsistent. In a real-world setting, oftentimes, if you're trying to make some changes in a data set that comes from some real-world thing, like shooting a target or manufacturing something, usually it's much harder to control variability than it is center. So C is centered up pretty well, pretty close to the center of the target, but it has much higher variability than B does. D is not only probably the most variable, it's definitely probably the farthest off center as well.